All right, we have looked at Newton's first law of motion, which doesn't involve any calculations. It's just a statement that says, Newton's first law, that if the forces are balanced, there's no acceleration. You can also repeat that a different way. If the forces are balanced, the velocity doesn't change. If the forces are balanced, then the object moves with a constant speed in a straight line, or it's not moving at all. Newton's first law also kind of implies what happens if the forces are unbalanced. If the forces are unbalanced, there's an acceleration. And Newton's second law quantifies that. Newton's second law gives us that formula that connects the net unbalanced force to the acceleration. We're going to take a break from Newton's second law, a one-day break, and then starting next week, we're going to be applying Newton's second law in a number of different ways. But I want to keep the sequence going here. We did Newton's first law, Newton's second law. Let's talk today about Newton's third law of motion, which you have been taught, but as you'll see with the examples today, the applications are more complicated at this level. We're going to look at what Newton's third law of motion is and apply Newton's third law of motion to find velocities, and we're going to also apply Newton's third law to find what are called reaction forces. So what a recap here. What Newton's first law says is an object will remain at a constant velocity, and that includes zero, unless acted on by an unbalanced net force. What's an unbalanced force? It's a force that's not counteracted by some other force. Okay? Newton's second law, as I said, quantifies that. And I don't have vector symbols up here, but you can put vector symbols if you like. Newton's third law deals with objects not in isolation. So when we talk about Newton's first law, maybe the forces are balanced on an object. Or we talk about Newton's second law, where maybe we have a net unbalanced force. When we think of those laws, we're always talking about one object. So when I describe the motion of a falling apple, we talk about the forces acting on the apple. But we don't talk about, when we're talking about the motion of the apple, what we don't talk about is the fact that the apple exerts a force on something else while it's falling. And this may be hard to believe, and we will understand more of it later in this unit, but the apple is attracted to the earth. That's not a big revelation, I hope. It's not a surprise. The earth attracts the apple, but forces don't occur just in isolation. If the earth attracts the apple attracts the earth. They're attracted to each other through something called the force of gravity. And whatever the force acting on the apple is by the earth happens to be equal to the opposite of the force acting on the earth by the apple. And now we're getting into Newton's third law. When we were talking about an object accelerating, like a car accelerating, we were only talking about the net force on the car, not the force on the road by the car. And Newton's third law brings this all together. If one object, I'm going to call it object A, exerts a force on object B, then object B must exert the same force but in an opposite direction to that first force. Maybe a simple way to look at this is when I'm playing baseball on the weekend and I swing and I hit the ball with the bat exerts a force on the ball. We know that because the ball, which was traveling towards me, all of a sudden travels in the opposite direction. It experienced an acceleration away from the bat. But if you've ever played ball, you know that no matter how fast you swing that bat, when it comes into contact with the bat slows down. Which means there's a force on the bat backwards. The ball is forced forward, the bat is forced backwards. It isn't just that there's some imaginary force that exists out of nowhere pushing the ball. The force is the force that the bat pushes on the ball with, and the ball pushes back on the bat with the same amount of force. And you can think of the force that the bat exerts on the ball as being the applied force, and you can think of the force that the ball exerts on the bat as being a reaction force. But they're both forces that are applied to each other. Examples. We're going to dive right in because some of these examples are pretty slippery. We need to spend some time talking about them. While standing on a horizontal frictionless surface, a 50-kilogram student pushes against a wall with an average force of 125 newtons east for 0.11 seconds. What's the velocity of the student at the end of that 0.11 seconds? Well, the force that the student pushes on the wall, this is a big subscript, the force that the student pushes on the wall is 125 newtons east. If we want to find, and let's just step away from that for a second. If you want to find the speed of the student at the end of the 0.11 seconds, then that means we're going to end up doing this bit of business again. VI equals, well, the student is just standing against the wall to begin with. They're on a frictionless surface. VF is the answer to this question. The time is 0.110 seconds. We don't know the distance they travel, and I don't know that we need to figure out the distance, and we don't know the acceleration. But and some of you are going to say that this question is no different than one we did yesterday, but it is different fundamentally, and I'm going to explain why. If you want to find this final speed or final velocity, then you need to know the acceleration, right? Which means you're going to have to make use of F net equals ma. And some of you are going to say, this is really tricky, really, as I say, slippery. Some of you are going to say, well, that's the force that they gave you in the question, but it's not. See, this is of the student. So the force we use has to be on the student. This force that I have written above is not the force on the student. It's the force that the student exerts on the wall, which means that the force on the student, this force right here, is actually 125 newtons west. And you might think that's an unimportant detail, and I'm telling you it's not. It's an important detail. So when we take that 125 newtons and set it equal, I'm going to put in the units here, set it equal to ma. I believe the mass of the student was 50 kilograms. And we calculate the magnitude of the acceleration, we need to keep in mind that the actual acceleration direction will be west. Because when the student, and I mean, think about it, if you're standing on ice and you push against the wall, then you're going to go backwards, right? So if I push the wall east, the wall can't move, I move west. So we can calculate what that is, and I believe that works out to 2.5. So the acceleration is 2.5 meters per second squared, and that is going to be west, and that's where Newton's third law comes in. And it's going to get trickier than this, but even there it's a little bit subtle. So we can put the 2.5 here. Since I'm including the direction, I guess I'll put a vector symbol above that. And then we want to find VF, so we can use A equals VF minus VI over T. I want to just explain this. I put vector symbols in this formula. I'm not going to put the direction in, though. I'm just going to do my calculation and then put west as an answer. Okay? Because if the acceleration is west, the final velocity will be west. You can see that VF minus VI is still going to be VF because VI is 0. So if I just multiply 2.5 by 0.11, I get 0.275, I believe. Is that right? So VF, the final velocity of the student, is 0.275 meters per second west. Any questions with that example? All right. This time we have a 75-kilogram student that's standing on a frictionless skating rink, and they're just standing there, and they're holding a 5-kilogram ball. It's over 10 pounds, about 12 pounds, some kind of medicine ball or something, and they throw it east at 10 meters per second. If you've ever fired a handgun or a rifle, if you hunt or you go target shooting, you know that you're not going to grab a rifle where this 3-hole punch is the butt of the rifle. You're not going to hold it here and pull the trigger. Because when the rifle pushes the bullet forward, the bullet pushes this backward. And you don't want to do that because it's going to hit you in the head. It's going to leave a mark. Probably permanent mark. Probably a scar. All kinds of videos on YouTube of dumb people doing exactly that. So if you're interested in seeing people get hurt, you know where to go. We know that, and this seems weird, if you were stuck on a skating rink, like it was frictionless, you do this and you just don't go anywhere, just take your phone and throw it, and you'll slide in the other direction. Because in order for you to throw your phone, you have to apply a force to the phone in one direction, which means Newton's third law says the phone pushes you backwards with the same force. Of course, your phone's going to be somewhere else, and you'll get off the rink, but maybe you can walk around the rink to get your phone. It's the same idea. So how do we do this? This is not a case where we can just do a series of calculations to get to the answer to the question. You pretty much have to build an equation here. What you have to do is say the following, that the net force, I won't even use the word net. I think that will confuse you. The force on the student and the force on the ball, I'm going to say they're equal right now, but I'm going to, you can write this down, but that's not true. That statement we've just written down, and I don't want you to erase it because we can make it true. That statement is wrong. It's false. And this is a minor detail. You may think it's minor, but it's actually a major detail. Why is that a false statement? Yeah. Going in different directions, right? The force on one is opposite to the force on the other, but what we can do is this. We can keep track of the directions and just forget about the directions in our work here. We can remember that the ball will be moving east and the student will be moving west. Exactly. And then what we're going to do is write MA here. So this is mass of the student times the acceleration of the student. And we've taken care of the direction by writing it off on the side. So these are absolute values. And this will be the mass of the ball times the acceleration of the ball. Well, that's really good, but we don't know any accelerations. We do know velocities. By the way, the initial velocity of the ball is 0, and the initial velocity of the student is 0. Because they're just standing there. Well, the student is standing there holding the ball. But I can take now, if I go to my formula sheet, I know acceleration is Vf minus Vi over t. And this is our first foray, our first exploration into building formulas from physics principles. We're going to end up with a formula here that is not on your formula sheet. And you may choose to memorize it, but I will tell you the result might be different in a different question. So memorizing formulas is not the way to go. Understanding physics principles and building them is the way to go. Well, what I'm going to do now is say this is the mass of the student times Vf minus Vi over t of the student. And I'm getting tired of writing absolute value signs, so I just drop the vector symbols. And over here we can write this is the mass of the ball times Vf minus Vi over t for the ball. So where do we go from here? Because we know the mass of the student and the mass of the ball, right? And I really want you to understand something. When we say they throw the ball with a speed of 10 meters per second, this is very subtle. If I throw a ball with a speed of 10 meters per second, I start with the ball in my hand and it's not moving. I accelerate the ball to 10 meters per second, and at that point I let it go. So the initial state has a velocity of 0. The final state of the ball is 10 meters per second east. You with me on that? Okay. And that means I can put in 5 well, let's not do that yet. We'll come back to that.
Please excuse the interruption, but with grade 12 students with the last names from A to C, please come to the office for your photos. That's grade 12 students with the last names from A to C. Please come to the office for photos. Thank you.
If at some point in this lesson you are called down, I'm not going to stop. I will post the lesson to my YouTube channel through Google Classroom, and you're responsible for the material. Okay. Vi is 0 here, right? So I'm just going to make a note that this is 0 and this is 0. So in the next line, we don't have to write anything. We know the mass of the student. We know the mass of the ball, and we know the final velocity of the ball. What don't we know in here that would stop us from finding the final speed of the student? Yep. The time. But I have that ball in my hand, whatever it is. I apply a force to the ball, and I apply a force from here to here. And whatever time that is, let's say it's 1 second. That means I'm applying a force to the ball for 1 second. But since that 1 second is when the ball and I part company, that 1 second is when the ball stops forcing me backwards. In other words, if I am applying a force to the ball for 1 second, the ball is applying a force to me for 1 second. If I'm applying a force on an object over a half-second interval, the object is applying a force to me over a half-second interval, which means that these cancel. And you end up with a very interesting result here, that the mass of the student times the final speed of the student will equal the mass of the ball times the final speed of the ball. And if you look at what we've done here, this is not a simple, I'm going to grab a formula off the formula sheet and throw numbers in. You have to understand what's going on here. But now we can put the numbers in. So as I said, this is the first time you built a formula. The mass of the student is 75 kilograms, so we have 75 times, we don't know their final speed, but that's what we are after. The mass of the ball is 5 kilograms times 10 meters per second. Did I get those numbers right from the top? Okay. So I have to take the 5 times the 10 divided by 75, and I get for a final speed 0.67 meters per second. So if you were asked for the final velocity, what is the velocity of the student at the end of this? It's going to be 0.67 meters per second. Was the ball thrown east? It was? That means the student moves west, so their final velocity is 0.67 meters per second west. Was that my calculation right there, 0.67? Okay. Any questions with the second example? All right, we have just a couple more, and these are difficult. Actually, this one's not bad. We've got 3 more. Did we just do this one? It's a different question. Okay. While standing on a horizontal frictionless surface, a 60-kilogram student throws a 5-kilogram object to his left. The object moves through a distance of 0.55 meters, reaching a final velocity of 6.7 meters per second. What's the velocity of the student when the object is released? I'm giving this to you just to highlight to you that sometimes you're given extra information. Look at the previous question. In the previous question, we knew both masses and the speed of the object, and we could calculate the speed of the person. That's what we're going to do here. The fact that it's 0.55 meters doesn't change a thing. So we can still do the following. We can still basically say that the force on the student is equal to the force on the ball. I'm saying ball, it's an object. I'll use O for object. Which means MA of the student equals MA of the object, which means M times your VF minus VI over T of the student equals M times your VF minus VI of the object, VF minus VI over T of the object. The times cancel, the initial speeds are 0, so you develop that formula again. MVF of the student equals MVF of the object. It's not a difficult question because we just did one exactly like it. Except this had added information. Do me a favor, you know the mass of both the student and the object, and you know the speed with which the object was thrown. Determine the velocity of the student afterwards for me. I'll show my work up here. That's the number I'm getting. So about 0.56. VF is 0.56 meters per second. I'm pretty sure I saw up there that the object was thrown to the left, which means the velocity of the student has a direction to the right. Any questions with example 3? All right, now things get complicated. So what we have are 3 boxes, and the boxes are on a frictionless surface. And they're not taped together or anything. They're just pushed against each other. We have a 7 kilogram box, a 9 kilogram box, and a 4 kilogram box. And you're going to apply a force to the whole thing. The hand is your hand. You're pushing on the whole thing, and the whole thing accelerates at 2.4 meters per second squared in the direction of that force. Okay? And the first question is, what is the force that C applies, what is the force on C applied by B? Okay? So would everybody agree that the third box accelerates, even though I'm not touching it directly? Okay. That must mean that there's a net force on C. What's applying the net force to box C? Well, it's not my hand because I'm not touching box C. It's box B. So if you were to look, and I'm going to ask you to draw these diagrams that I draw, and you have more than enough room, but I have to wait for my computer to catch up. I'm going to ask you to draw box C right now, someplace. What we want to do is analyze the forces on box C. So, for example, I'm asking you to draw box C someplace. We can put a line for the floor if you like, although it's not necessary. But this is box C. Now, what are the forces acting on box C? Well, there's only one force acting on box C. The force acting on box C is a force in this direction. And this is the force on C by B. And for the remainder of this unit, things are going to get a little wild, a little difficult. So I want to go slow. And don't roll your eyes and go, oh man, I get it. Things can really change quickly here. This is the force acting on C by box B. It's the force that B is exerting on C. Are there any other forces on C? Well, no, because nothing else is touching C, and you're told there's no friction, so that's it. But what that means is that this is the net force on C. Listen very carefully. If this is the only force acting on C, then it's the net force, because net means add them up. Okay? So this is the net force. So how do we calculate the force on C by B? Sorry. How do we calculate this force on C by B? We calculate the net force. Yeah. I'll post the link too. We calculate this net force. F net, this is on C, is equal to the mass times the acceleration. So that is how many kilograms? 4 kilograms times the acceleration. Did I see that everything accelerates at 2.4? So times 2.4, which gives me, I believe, 9.6 newtons. Yes? Okay. So the answer to the first question is 9.6 newtons. Now, let's do the same thing with box B, but it's not going to be as simple. Okay? When you take a look at box B, this is box B. Shouldn't have picked that. We'll wait for it to catch up again. This is box B, and box B has a mass of 7 kilograms? 9. Okay. So this is box B, which is 9 kilograms, here's the floor, is B being...
Grade 12 students from A to M, please come to the office for your pictures. That's grade 12 students with the last name J to M. Please come to the office to pick up your photo. Thank you.
Is B being forced to the right? Yes. By what? By A. So when we draw this force, this is the force on B by A. And I want to back up and show you the diagram for C again, and I know I'm going very slow. By the way, when I go very slow like this, it's because I have to think it through. This is not simple. So that's something that you should take away from this. I want you to notice that the force I drew, although it happened to be the net force, is an applied force. I didn't draw the net force on there. I drew the force that was applied. And because there was no friction, this force was the only force, and that's the net force. I'm going to ask you an incredibly difficult question. Why is this force that A is pushing on B with not the net force? Wow, I've done a pretty good job then if some of you know right away. Yep. Right. Box C is pushing back on box B. Over here, we've calculated that B is pushing on C with a force of 9.6 newtons to the right. But Newton's third law says then that B must be pushed backwards from C with the same force. So this is the force on B by C. So if I say to you, is this the net force? The answer is no, because there's another force. If I say to you, is this the net force? No, because there's another force. What's the net force? It's the sum of these. So the net force, and there's so much going on here that I have to teach you. Notice I've dropped the vector idea here. I'm just saying the magnitude, and I'll even put this in, the magnitude of the net force will be equal to the magnitude of the force on B by A minus the magnitude of the force on B by C. So we're going to come back to this recurring theme, everybody. Often we can take physics problems and tear them down into a force and an opposing force. And the net force is the force minus the opposing force. By the way, how do I know that the force on B by A is bigger than the force on B by C? No, it's not because of the masses. That's one way to look at it. The bottom line is the boxes do accelerate to the right. So each box must have a net force to the right. Very quickly here, Ashley, we're looking at box B, and box B is being pushed to the right by box A. But unlike this situation here, where this force on box C by B was the net force, it was the only force, here, since C is being pushed by B, B is pushing back on C. And this is the 9.6 newtons that we got for the force on C by B. So what that means is the net force is that. And we can build an equation. We can say that MA, I can't stress this enough, MA is always the net force. It's always the net force. It might be other forces from time to time, but it's always the net force. Equals the force on B by A minus the force on B by C. And we can put some numbers in. The mass of box B, you said, was 9 kilograms. So 9 kilograms, well, it accelerates at 2.4, equals equals the force we're trying to find. Minus the 9.6 newtons. I want to back up. Let's just stop for a second. Look at what I wrote there. What is the force on C applied by B? I should have written this. Would you agree? What's the answer to what is the force on B applied by C? Yep. The opposite. Okay. And what we're working on is the force on B applied by A. So you don't want to cheap out on the subscripts. I dropped the word "and" here.
Excuse the interruption. With grade 12 students with the last names N through R, please come to the office to pick up your picture.
We don't want to cheap out too much on the subscripts. I admit I dropped the word "and" here, but you don't just want to go FBA. Like you want to know which object is being forced. So I need to take 9 times 2.4 and add 9.6 to solve this equation. I want to say 31.2, but apparently I'm wrong. 18. 30.8. I'll just 31.8. 31.2. You know, if I shouted out random numbers sooner or later, I would get it. 31.2. So on B by A is 31.2 newtons. And look at the diagram. It's to the right. So we can write that in our list of answers. 31.2 newtons, right? And that means if the force on B applied by A is that many newtons to the right, then we have 31.2 newtons on A applied by B to the left. Now, what is the force on the hand? I'm going to do these in opposite order. What is the force on A applied by the hand? Let's do that first. Okay. So now I'm going to draw box A. Probably a mistake. Too late. Nope. I'm going to draw box A. Here's box A. Here's the floor or the ground. And I really believe it's important for you to draw each of these separately. I think if you try to put all these forces on the same diagram, it's a nightmare. Well, this box A does move to the right. By the way, the length that I'm drawing these is not scaled or anything. It's just to the right. And this is the force on A by the hand. Is that the net force on A? No. Because since A was applying a force to B of 31.2 newtons to the right, B was applying a force on A of 31.2 newtons to the left. So this is the force on A by B. And you know, there's nothing wrong with you putting 31.2 newtons up here. There's nothing wrong with you actually writing this number up there. So what does that mean? It means the net force on A will be equal to, we'll have a magnitude that's equal to the magnitude of the force on A by the hand minus the magnitude of the force on A by B. So we get, this is MA. I'm not going to rewrite the whole thing just to write MA here. This is is A 7 kilograms? No. 7 kilograms times, well, A accelerates at 2.4 meters per second squared. We're after the force on A by the hand minus that 31.2 newtons. So you have to take 7 times 2.4 and add 31.2. I want to say 48. So you get 48 newtons, which means that the force on A by the hand is 48 newtons, and that would be to the right. Going back to the question, that means this is 48 newtons right, and the force on the hand by A is 48 newtons left. And I have one more thing to do here before we polish off this lesson. I want you now, so I'll pause there. Any questions with that? It's a complicated process. It's not really simple. Go ahead.
Why would C also be affected?
Because C is not contacting A directly. Now, I admit we're cheating the system here. It's a great question. But this leads to what I'm going to ask you. Treat this thing as I said these boxes were not taped together. Treat them as if they were glued together. What's the total mass? Figure out what the total mass is. 20 kilograms? So, if I accelerate 20 kilograms at 2.4 meters per second squared, what net force is required? .48 newtons. Well, that's the force that the hand is pushing on the whole thing with. It's a weird situation. And speaking of push, I don't want to push my luck. We're not going to do this example today, example 5. What we will do is on Monday we will do example 5, and I think I'm going to try to set up a lab where we measure some forces and look at balanced forces, okay? So for your assignment, you are going to do on the handout 1 to 6. You're not going to do 7 because 7 is like the example we're skipping over today. So the assignment, questions 1 through 6 in your handout. We're not going to move on to the next lesson on Monday. On Monday, we're going to do a bit more work with forces in this context, and we're going to do a lab of some kind. I got to figure out what to do, but we'll do something, okay?